Question 1. A solid cylinder of mass m and radius r rolls without slipping down a uniform slope. The slope makes an angle theta to the horizontal, and what we can see is the diagram shows three forces acting on the cylinder. N is the normal reaction force, F is the frictional force between the cylinder and the slope. A. State why F is the only force providing a torque about the axis of the cylinder. The axis of the cylinder is here, and now you'll remember that the equation for torque is FR sine theta. R is the distance from the axis, and you'll notice that N acts from the axis and mg acts from the axis. So for both of those forces, the distance from the axis is 0. That means that their torque is 0. F is the only force that acts a distance from the axis. That's our answer. F is the only force that acts a non-zero distance. Actually, we shouldn't really write just the word distance when we're talking about torque. We should write the word perpendicular distance from the axis. Why should we write the word perpendicular distance from the axis? Because actually that's all we're interested in. If you imagine we have an axis here and a force acting on a rod there, we're actually interested in this distance here because it's the component of force that acts perpendicularly to the axis. So when you're talking about distance from the axis in torque, I would always talk about the perpendicular distance from the axis. B1. The moment of inertia of a cylinder about its axis is this. And remember, I did tell you, you'll probably be given the formula for the moment of inertia. You don't really have to remember them. It's useful to, but you don't have to remember the formulae for moment of inertia. Show that by applying Newton's laws of motion, the linear acceleration of the cylinder is A equals 2/3 g sine theta. This is one of the difficult problems I was talking about in step 1 mass of the majority, and you can see it's worth 4 marks. But it's the same process every time, and this is not the first time we'll be seeing this question. We start with finding an equation for the linear acceleration using Newton's second law. So linear Newton's second law is F equals ma. We have to be a little bit more specific here. We've got the slope, we've got the ball, mg. F is the net force that causes the acceleration. And the net force that causes the acceleration on this ball is the force down, mg sine theta, the force down the slope, minus the frictional force. So instead of writing F equals ma, it actually becomes mg sine theta minus friction equals ma. That's our linear equation using Newton's second law. Then we use our angular equation using Newton's second law, and that is torque equals inertia alpha, and alpha is the angular acceleration. Let's expand on that a little bit. We know that torque is equal to Fr, and does that work? Let's go to the diagram. F is the force, R is the distance from it. Yep, so torque is equal to Fr. We also know that the moment of inertia is a half r squared. And we know that alpha is equal to, and remember I told you about this relationship, A equals alpha r. If we have an object that's got angular and linear acceleration, we can link them with that equation. So instead of alpha, we're going to put A over r. Let's simplify that out a bit. Well, that r cancels with that. So we've got m r A over 2. We can actually simplify that even further because we've got an r on either side. So r. So F equals ma over 2. That F is the same as this F here. So we're going to substitute this into here. Let's do it. mg sine theta minus ma over 2 equals ma. Let's take that over to there. mg sine theta equals ma A plus half ma, which equals 3 over 2 ma. There's an m on both sides, so let's get rid of that. What that gives us is g sine theta equals 3 over 2a, and rearrange for a equals 2 over 3 g sine theta. We did it! That's not the first time you'll see that interlinking of linear and angular Newton's second laws. You'll see it with pulleys as well. So it tends to be objects rolling on a slope or pulleys. B2. Calculate for theta equals 30 degrees the time it takes for the solid cylinder to travel 1.5 metres along the slope. The cylinder starts from rest. Okay, we're going to use the equation from before, which was A equals 2 over 3 g sine theta. That goes to 2 over 3 g half, because sine 30 is equal to 0.5, which gives us 1/3 g. I'm just going to leave it like that just now. I'm not going to put 9.81 in there just yet. Okay, so we now have the acceleration. We want to find the time. We're going to use SUVAT equations, aren't we? SUVAT. We know that the length is equal to, or the distance is equal to 1.5 metres. It starts from rest, so this is 0. V, we don't know, we don't really care. A is equal to 1/3 g, and t is what we want to know. So S equals ut plus 1/2 at squared. 1.5 equals 1/2 times 1/3 g times t squared. We rearrange all that, and that gives us that t equals the square root of 9 over g. And now if we put 9.81 into there, it gives us t is equal to 0.9578 seconds. All the data is given to two significant figures. So we're going to bring that down to two significant figures, which is 0.96 seconds. I knew to use linear equations there because there was linear data given, and the question before had given us a value for linear acceleration, so linear stuff was in my mind. C. A block of ice is placed on the slope beside the solid cylinder, and both are released at the same time. The block of ice is the same mass as the solid cylinder and slides without friction. At any given point on the slope, the speed of the block of ice is greater than the speed of the solid cylinder. Outline why using the answer to B1. The answer to B1 was 2 over 3 g sine theta, and that's for the cylinder. Can we find an expression for A for the block? Well, let's try that, because then we can compare them, you see. The block of ice, it will have a force acting down the slope of mg sine theta. There's no friction. Okay, so the force causing acceleration is F equals ma, so it's mg sine theta equals ma, the m's cancel. So the acceleration for the block is A equals g sine theta. That's bigger than 2/3 g sine theta, so A of the block is greater than A of the cylinder at all times. Therefore, if the acceleration is greater and they both start from rest, then the velocity of B is always going to be greater than the velocity of the cylinder. D. The solid cylinder is replaced by a hollow cylinder of the same mass and radius. Suggest how this will affect, if at all, the acceleration in B1. Okay, the moment of inertia of the solid cylinder we were given, and it was 1/2 mr squared. Do you remember in step 1, mass of the majority, I told you this really weird thing that the moment of inertia of something hollow is always greater? And in fact, you don't need to know the equation to this, but the moment of inertia of a hollow disk is actually mr squared. It's bigger than the solid one. So if we know that I hollow is greater than I solid, and we can go back to B1 to find out how the moment of inertia affected the acceleration. And you'll remember that we had mg sine theta minus tau equals ma. And then what we did was we took tau and we said tau equals I acceleration. Okay, there's I. We also had this relationship. So let's rewrite that. mg sine theta minus moment of inertia A over R equals ma. mg sine theta equals ma plus moment of inertia A over R. And I don't think we have to go any further, because what's ultimately going to happen is that A equals mg sine theta divided by a factor on this side. Okay, and that factor includes I, right? And if the I for the hollow is greater than the I for the solid, then this number here is going to be smaller. So the answer is the acceleration for the hollow cylinder will be smaller than the solid cylinder, because the moment of inertia hollow is greater than the moment of inertia solid. Question 2. A flywheel consists of a solid cylinder with a small radial axle protruding from its centre. Just having a very quick look at this diagram, we'll see that this M will have linear acceleration and there will be angular acceleration of this flywheel. The following data is available for the flywheel. An object of mass M is connected to the axle by a light string and allowed to fall vertically from rest, exerting a torque on the flywheel. A. The velocity of the falling object is 1.9 meters per second at 3.98 seconds. Calculate the average angular acceleration of the flywheel. So we've got some linear data given and we want to find the average angular acceleration. So let's find, using SUVAT, the linear acceleration first. We've got some data for that, haven't we? So V is equal to 1.89 meters per second. A we don't know. Time is 3.98 seconds. We can use V equals U plus AT, which gives us an expression for A, and that is 1.989, divided by 3.98, which gives us a linear acceleration of 0.4748 meters per second. We'll put that to the correct number of significant figures in a moment. We know that A equals alpha R. Alpha equals A over R. A is equal to 0.4748. And R, well, what radius are we going to use? Well, the radius, we're going to use a small radius because the linear acceleration is coming from that small radial axle. And the small radius is 60 millimeters, so 60 times 10 to the minus 3, which gives us an answer of 7.91 radians per second squared. B. Show that the torque acting on the flywheel is about 0.3 Newton meters. I know two equations for torque. I know this one and I know this one. To use this one, we'd need to know what F is, which is the weight of the small mass that's pulling on the side of the object. And actually we don't know the mass of that. Okay, so we can't use this equation. We have to use this one. We do know what the angular acceleration is. That's 7.91 radians per second squared from the previous question. And we can find out what I is using the moment of inertia for a disc, which is a half mr squared. So it's a half times the mass of the flywheel, which is 1.22, times the radius squared of the flywheel, which is 240 millimeters squared, which gives us a value of 0.0351 kilograms meters squared. Okay, now we can put it into tau. Tau equals I alpha, which is 0.0351 times 7.91, which is 0.2779 Newton meters. That gives us 0.3 Newton meters as requested. C2. Calculate the tension in the string. So remember, we've got a little flywheel here. We have the tension in the string that's causing that flywheel to rotate at a radius. And I think we can use torque for that, because torque is equal to FR sine theta. And F is actually tension in this case. F is the force that's causing this torque. So torque equals T r sine theta. Torque we know from above, which is 0.0351, equals tension times the radius of the flywheel, which was smaller, it was 60 millimeters, times sine 90, which is 1. So T equals 0.0351 divided by 60 millimeters, which gives us a value of 4.63 newtons. So the tension in the string is 4.63 newtons. If we wanted to put it to the right number of significant figures, it would be 4.6 newtons. And determine mass M of the falling object. We've never known what M is. Let's draw a diagram of this pulley. We know that mass M is accelerating downwards, so we're going to use our version of Newton's second law here. And this is the net force acting on the mass that causes it to accelerate downwards. And that net force is equal to mg minus t equals ma. If you don't know that, head to my pulleys tutorial in A2. So now we've got somewhere. We know that tension is equal to 4.63 newtons. We worked that out in the previous question. We know what G is, obviously. Do we know what A is? We actually know what A is because we worked that out in the first question. It was 0.4748 meters per second squared. We have enough data to solve for M now. 9.81 M minus 4.63 equals 0.4748 M, or 9.81 M minus 0.4748 M equals 4.63, and we can work out that M equals 0.4959 kilograms. M equals 0.50 kilograms. If you found getting step 1 difficult, I suggest you head to my pulleys tutorial in A2. Question 3. The diagram shows two methods of pedalling a bicycle using a force F. In method 1, the pedal is always horizontal to the ground, which means there's always an angle between the crank arm and the force. A student claims that method 2 is better because the pedal is always parallel to the crank arm. Okay, the pedal is always parallel, which means the force is always perpendicular. Explain why method 2 is more effective. Well, let's look at method 1 first. With method 1, say we have the position here and the position there as examples, and we have the force acting at these points each time. This is the axis or the pivot. The perpendicular distance to the pivot, which I talked about earlier, perpendicular distance to the pivot changes, it varies as it goes through that quarter circle. Perpendicular distance to pivot changes. And what does that mean? Well, the torque is equal to F r sine theta. This F is the same, but r sine theta changes because the angle of the force and the perpendicular distance to the pivot, which is basically r sine theta, changes. So the full 90-degree angle of force is not always applied. We'll write that down. With method 2, we look at method 2, then the force is always sine 90, and tau equals F r sine 90. The distance, perpendicular distance to the pivot doesn't change either. So this is constant at its maximum value. So for method 2, the force is always applied at maximum r sine theta 90. So the maximum force is always going to be applied. So method 2 is more effective. Now, when I'm thinking about it, I've got no idea how he's going to apply a force that way. And that is where this method 2 falls down, because this method only really works within that quarter, doesn't it? You can't apply a force up at 90 degrees with your foot that way. So this is a very specialised question, I would say. Question 4. Wow, there's lots of writing in this, but I bet you it ends up being quite simple. Okay, A horizontal rigid bar of length 2r is pivoted at its centre. The bar is free to rotate in a horizontal plane about a vertical axis through the pivot. A point particle of mass m is attached to one end of the bar and a container is attached to the other end of the bar. A point particle of mass m/3 is moving with a speed v at right angles to the rod and collides with the container and gets stuck in the container. The system then starts to rotate about the vertical axis. The mass of the rod in the container can be neglected. Okay, so we're really only interested in this mass here, which is m/3, and that's not initially in the system, and then this mass here, which is m, which is in the system. Write down an expression in terms of m, v, and r for the angular momentum of the system about the vertical axis just before collision. Okay, just before collision, the rod and the mass m is travelling with 0 angular momentum. Okay, and we know that angular momentum is I omega, and if omega is 0, then the angular momentum of the rod and the m is 0. So we don't have to worry about that. However, this mass here will have angular momentum, and let's work out what that is. L equals I omega. We can work out what the moment of inertia of the mass is using this equation here, which is in our data booklets, mr squared. The mass of the object is m/3, and r is the distance from the pivot, and in this case actually is r because the length of the rod is 2r. So our moment of inertia for the mass that's approaching this pivot is mr²/3. We can also work out what the angular speed of this object is using the expression that we learned in A2, v equals omega r. So omega equals v/r. And actually that works because the linear speed of this object is v, the distance from the pivot is r. Great, so we've got an expression for I and we've got an expression for omega. Let's put them into the expression for angular momentum. L equals mr²/3 and omega equals v/r. So L equals mrv/3. That's our answer. A2. Just after the collision, the system begins to rotate about the vertical axis with angular velocity omega. Show that the angular momentum of the system is equal to 4/3 mr² omega. We have to do a very similar thing as before, but this time we want to find out the angular momentum of the whole system, and L is going to equal to I omega. But we have to find out the moment of inertia of the whole system now. And the moment of the inertia of the whole system is going to be used calculating this equation, which we found in the data booklet. And that's the sum of all the moment of inertias. We know that the moment of inertia of the small mass is m/3r². And we know that the mass of the mass on the other side of the rod is mr². If we add those both together, that gives us 1/3 plus 1 mr², which gives us 4/3 mr². And we know that I is equal to that. So now our expression for the angular momentum is 4/3 mr² omega, because the angular velocity of the whole system is omega. That is our momentum after. Aha! Hence show that omega equals v/4r. I think we're going to use this expression. Momentum before equals momentum after. The momentum before, of course, was mrv/3 equals momentum after, which is 4/3 mr² omega. 3 can cancel, m can cancel, one of the r's can cancel, and what we're left with is v equals 4r omega. So omega equals v/4r. Gosh, that's quite a lot of work for 1 mark each of those questions. There we go. Determine in terms of m and v the energy lost during the collision. Well, energy before is equal to 1/2 I omega squared, which gives us 1/2, and the I before was mr squared over 3 times omega squared, and that was v over r all squared. We want to simplify this down now. Well, a half times a third is a sixth, so that takes numbers out of it. This is going to be r squared, and that's going to be v squared. So those two r squareds will cancel. What we have is mv squared. Oh, that's it. So the EK before is equal to a 6 mv squared. Let's see what the EK after is. Equals a half I omega squared, 4 over 3 mr squared. And omega squared, and omega after was v over 4r, so v over 4r all squared. Let's simplify that down. A half times 4 over 3 times mr squared v squared over 16r squared. That cancels. And we have a half times a 16th times 4 over 3 gives us 1 over 24 mv squared. So our change in kinetic energy is equal to the EK before minus the EK after, which is 1 over 6 mv squared minus 1 over 24 mv squared, and that gives us a value of 1 over 8 mv squared. Again, quite a lot of marks, but that was 3 marks this time, so I feel like it was worth it. A torque of 0.01 newtons brings the system to rest after a number of revolutions. For this case, R equals 0.5 meters, M equals 0.7 kilograms, and V equals 2.1 meters per second. B1, show that the angular deceleration of the system is 0.043 radians per second. Wow, okay, we're going to use this equation here. And that, of course, is derived from the angular version of Newton's second law. The torque is Fr sine theta, and the moment of inertia of the whole system we calculated way back, which was 4 over 3 r squared. So we're going to pop that down here, 4 r squared, and that 3 goes back up here. And how can we answer the question there? Well, Fr sine theta is equal to torque, so it's 3 times 0.01 divided by 4 times the mass, which is 0.7, times r squared, which is 0.5 squared. Pop that all into the calculator and we get 0.0428, which gives us 0.043 radians per second squared, as mentioned in the question. 2. Calculate the number of revolutions made by the system before it comes to rest. Okay, my instinct here is to use the equations of motion, but the angular version. And for that, I'm going to write down all these different things. Because the number of revolutions is basically a value of how many times it goes round, which is going to be this change in angular displacement. So I think we want to know what that is. We know that the initial velocity before it stops is equal to v over 4r, which is 2.1 divided by 4 times 0.5, which is 1.05 radians per second. Its final angular speed is going to be 0. Our acceleration we worked before is 0.043. That we can work with that. We're going to use this equation. Final angular velocity squared equals initial angular velocity squared plus 2 alpha change in angular displacement. It's a bit of a mouthful, isn't it? But there we go. 0 equals 1.05 squared plus 2 times 0.043 times change in angular displacement. That means that the change in angular displacement is equal to 1.05 squared divided by 2 times 0.043, which gives us an answer of 12.82 radians. Now, to find the number of revolutions, what we have to do is divide that by 2 pi, which gives us a value of 2.04 revolutions. Question 5. A cylindrical space probe of mass 8 times 10 to the 2 kilograms and diameter 12 meters is at rest in outer space. Rockets at opposite points on the probe are fired so that the probe rotates about its axis. Each rocket produces a force of 9.6 times 10 to the 3 newtons. The moment of inertia of the probe about its axis is 1.44 times 10 to the 4. A1. Deduce the linear acceleration of the centre of mass of the probe. Well, the word deduce here is used and is 1, so I know this answer is pretty simple. It's also pretty simple because when these rockets start to fire, this space probe is going to rotate very, very quickly. But it's not going to move, the axis is not going to move in any direction. It's simply going to cause angular velocity. That means that the linear acceleration of the centre of mass of the particle is 0. A2. Calculate the resultant torque about the axis of the probe. Torque is equal to Fr sine theta. F is the force produced by the rocket probe, which is 9.6 times 10 to the 3. R is the radius, which is 6 meters. For one rocket probe, the torque is 57,600 Newton meters. For 2 rocket probes, it's twice the amount of that. So the sum of the torque is equal to 2 times 57,600, which gives us 115,200 Newton meters. Let's make that look a bit nicer. 1.152 times 10 to the 5 Newton meters. The forces act for 2 seconds, show that the final angular speed of the probe is about 16 radians per second. I think we're going to use our equations of motion for angular properties. We do have, what do we have? The time. We know that initially it starts at 0. We want to find out what the final angular speed is. We've got torque, which is 1.152 times 10 to the 5. And we've also been given the moment of inertia for the system, which was 1.44 times 10 to the 4. That means we can work out what the angular acceleration is. 1.152 times 10 to the 5 divided by 1.44 times 10 to the 4 gives us an angular acceleration of 8 radians per second squared. So that goes to 8 rads per second squared. We then go to our data booklet and look for the appropriate equation of motion, and we're going to use omega F equals omega I plus alpha T. Omega F equals omega I, which is 0, plus alpha, which is 8, times 2, which is 16 rads per second squared. C. The diagram shows a satellite approaching the rotating probe with negligibly small speed. The satellite is not rotating initially, but after linking to the probe, they both rotate together. The moment of inertia of the satellite about its axis is 4.8 times 10 to the 3. The axis of the probe and the satellite are the same. Determine the final angular speed of the probe satellite system. Okay, when this probe joins with that satellite, that's the equivalent of a collision. So what we're looking at is the angular momentum before the system and the angular momentum after the system. We know they are the same because of the conservation of angular momentum, which will allow us to find the final angular speed. Let's write down the expression for the conservation of angular momentum. We know this is 16, we just calculated that before, and we also know that this is 1.44 times 10 to the 4. We were told that in the question. We can work out the final moment of inertia by adding the moment of inertia of the initial system to the moment of inertia of the satellite, which will give us a value of 19200. 19200. Let's rearrange for the final angular speed, which is I omega I over IF. So 1.44 times 10 to the 4 times 16 divided by 19200, which gives us a value of 12 radians per second. 2. Calculate the loss of rotational kinetic energy due to the linking of the probe with the satellite. Okay, well the EK before is equal to a half I omega squared, which is a half times 1.44 times 10 to the 4 times 16 squared, which gives us a value of 1843200 joules. The EK after the collision is half omega squared as well, which is a half times 19200 times 12 squared, which is 1382400 joules. The change in kinetic energy is those two values subtracting each other, which gives us a value of 460,800 joules. Make that nicer. 4.61 times 10 to the 5 joules. Question 6. A hoop of mass m and radius r and moment of inertia mr squared rests on a rough plane inclined at an angle of theta to the horizontal. It is released so that the hoop gains linear and angular acceleration by rolling without slipping down the plane. A. On the diagram, draw and label the forces acting on the hoop. Well, the first force acting on the hoop is weight. That comes from the centre of mass of the object. Call that weight equals mg. The second force that acts on the hoop is the normal reaction force. That is perpendicular to the surface. That's called N. And the third force acting on this is the frictional force, which acts between the surfaces and it opposes motion. Aha! Show that the linear acceleration of the hoop is given by. This is exactly the same as it was before. So linear acceleration. We use Newton's second law for that, which is F equals ma. This F is the net force, and the net force causing the acceleration is mg sine theta minus friction equals ma. Angular acceleration. The torque provided on this hoop is provided by the frictional force because it's the only one that acts as a distance away from the axis. So the angular acceleration, the expression we want to use for that is tau equals I alpha. Tau is the torque, which is Fr equals I alpha. I given before was mr squared. Alpha, and of course we know that alpha is the angular acceleration. That is related to the linear acceleration with this expression here. So Fr equals mr squared a over r. And we want to just get an expression for f so we can pop it back into the equation above. So F equals mr squared a over r squared, because we're taking that r down to there. These cancel. F equals ma. Fine. Let's go to here now. mg sine theta minus F equals ma. ma equals ma. So mg sine theta equals 2ma. Take that over to that side. Therefore, A equals mg sine theta divided by 2m. These cancel. A equals g sine theta over 2, which is the answer shown there. And that should be theta, obviously. We've done that before. It is worth 4 marks, but it's the same system every time. So make sure you learn how to do that system. C. Calculate the acceleration of the hoop when theta equals 20 degrees. Assume that the hoop continues to roll without slipping. Well, we're going to use this expression up here. G sine theta over 2, which is 9.81 times sine 20 over 2, which gives us 1.68 meters per second squared. D. State the relationship between the force of friction and the angle of incline. So we want to find a relationship between F and theta. The normal force is mg cos theta. And frictional force has the equation of that, doesn't it? Okay, so the frictional force is equal to mu on normal force mg cos theta. Oh, that works. But it's not equal. Frictional force is less than or equal to mu on mg cos theta. There we go. E. The angle of incline is slowly increased from 0. Determine the angle in terms of the coefficient of friction at which the hoop will begin to slip. Okay, so at the point where the force acting down the slope equals the frictional force acting up the slope, that's the point where the hoop will begin to slip. Now, the force down the slope, F equals ma, we know what the A is because we calculated that in the first question. We were told that F equals m, and what was the expression? A is g sine theta over 2. So g sine theta over 2. That's the force acting down the slope. The frictional force is the one above, which is mu on mg cos theta. And when these two are equal to each other is when it will start to slip. So let's put them together. Mg sine theta over 2 equals mu on mg cos theta. Let's cancel those mg's out. Mu on equals half sine theta divided by cos theta. And of course, by maths, we know that sine theta over cos theta equals tan theta. So mu on equals a half tan theta. That is our expression. Question 7. A constant force of 50 newtons is applied tangentially to the outer edge of a merry-go-round. The following diagram shows the view from above. The merry-go-round has a moment of inertia of 450 kilograms meters squared about a vertical axis. The merry-go-round has a diameter of 4 meters. Show that the angular acceleration of the merry-go-round is 0.2. We want to find out what that is. We don't have any information like initial angular speed or whatever, so we can't use the equations of motion, but we can use tau equals I alpha. And we know that tau is the torque, and that's going to be FR sine theta. Were we given force? Yeah. 50 newtons times 2, so the torque is 100 newton meters. That means that alpha equals tau over I, which is 100 over 450, which gives us a value of 0.2 radians per second squared. B. The merry-go-round starts from rest and the force is applied for one complete revolution. Calculate for the merry-go-round after one revolution the angular speed. Now we're going to use these equations of motion because I'm seeing things like from rest, which is the initial angular speed, one complete revolution, which means that this is 2 pi, and we've also got angular acceleration. So we have equals 2 pi, omega I equals 0, omega f equals, I want to know what that is, alpha equals 0.2, and time, not too fussed about. We're going to use this equation here from our data booklets. Omega f squared equals 2 times 0.2 times 2 pi, which means that omega f equals the square root of all that, which gives us a value of 1.67 radians per second. B2, calculate the angular momentum. L equals I omega. I is 450, we were given that in the question, times 1.67, which we've just worked out, and that gives us 751.98 kilograms per meter squared radians per second. And of course, that's far too many decimal places and significant figures. Let's just bring it down to 752. A child of mass 30 kilograms is now placed on the edge of the merry-go-round. No external torque acts on the system. We're looking at conservation of angular momentum here. Big clue. There's been a change in the system, so an extra mass has been added. It's like a collision, and no external torque adds. Calculate the new speed of the rotating system. Okay, so L before equals L after, And we know that L before is equal to 7. Let's just use the very accurate number. Equals the moment of inertia after times the angular speed after. The moment of inertia after. Right, well, we know that the moment of inertia before was 450, but now we have to add on the moment of inertia of the child. So that will be 30 times, and the child was added at the edge of the system. So they were added at a radius of 2, which gives us 450 plus 120, which gives us 570 kilograms meters squared. So the final angular speed is equal to 751.98 divided by 570, which gives us a value of 1.37 radians per second. D. The child now moves towards the centre. 1. Explain why the angular speed will increase. Well, we know that the momentum before was equal to the final moment of inertia times angular speed. So angular speed afterwards is equal to the momentum before divided by this new moment of inertia. This doesn't change, it's the same. But if we move the child towards the centre, the final moment of inertia will be less than before. So if the final moment of inertia is less, that means that the final angular speed will increase. That's why. 2. Calculate the work done by the child in moving from the edge to the centre. Work done. Do you remember I told you in A3, always write down work done equals energy transferred. What this is asking is, what is the change in kinetic energy when the child is moved from the edge to the centre? So the kinetic energy at the edge is equal to a half I omega squared, which is a half times 570, which is the new moment of inertia. Let me just check. Yep. Times 1.37 squared, which was the angular speed. That gives us a value of 131 joules. Now, the kinetic energy at the centre is actually going to be 0 because this is made up of mr squared, and r is the distance from the axis, which is 0. That makes this whole thing 0. So the kinetic energy of the child at the centre is 0. That means the work done is equal to 131 minus 0, which is 131 joules.